Thank you all for coming out. As Katie mentioned, I'm a researcher at the SETI Institute. I work on Mars exploration, worked on some of the rovers during my undergrad years, Spirit and Opportunity, mapping color images of Mars, understanding how the geology forms, using satellites to look at spectroscopy, to look at the minerals throughout the planet, trying to figure out where our next rovers are going to land by mapping where we're going to go and why we're going to spend $10 billion over the next few years to pick back 100 grams of rocks. All those things that NASA likes to spend our tax money on to explore the universe. So yeah, I'm going to talk a little bit about like our journey to Mars, what we've, how we turned this concept of Mars as a point of light in the sky into a world that our rovers are on, that people like me spend all day thinking about, and the technologies that we can use to share that knowledge with the world and possibly build a self-propagating future there. So beyond doing science research at the SETI Institute, just up the road by NASA, actually we're closer to NASA than SETI is, but it's still pretty close. Working with a company made of Mars, which has working with materials. That was a collaboration I did with Kitty, and I'll talk more about that and welcome you to come up and feel some objects, and working as the chief science officer of a company, Astro Reality, that's making models of the solar system, as well as notebooks, and using augmented reality to try and share some of this data that NASA's created. So all these products here are meant to feel, and especially the models of the planets, we want you to feel the texture, the mountains, the craters, the canyons. And so if you feel like you want to grow up and grab one and feel it during the talk, feel free to grab that, bring it back to your chair, and pass it to your neighbors. As long as they all end up back here at the end of the day, I'm happy with you guys feeling all the features, because that's the point, is to try and make these planets into something in your hands, something real. So as we go on, I kind of want to skip to the very end of what can be. What is like the vision of what we're trying to do? And one of my favorite ways to do this is this wonderful video of real places in our solar system and what they might look like with a human future beyond Earth. So it's this amazing little video of called The Wanderers that imagines what this future might be. And for some reason, they want to give me errors. So it will be a few minutes. And so again, the key factor here is that every place that you see in this is a real place that we can dream of going if we can get the money, the technology, and the human will to go. And I want to set this vision, and then we can talk about the actual steps to get there.
For all its material advantages, the sedentary life has left us edgy, unfulfilled. Even after 400 generations in villages and cities, we haven't forgotten. The open road still softly calls, like a nearly forgotten song of childhood. We invest far-off places with a certain romance. The appeal, I suspect, has been meticulously crafted by natural selection as an essential element in our survival. Long summers, mild winters, rich harvests, plentiful game. None of them lasts forever. Your own life, or your band's, or even your species might be owed to a restless few drawn by a craving they can hardly articulate or understand, to undiscovered lands and new worlds. Herman Melville in Moby Dick spoke for wanderers in all epochs and meridians. He said, "I am tormented with an everlasting itch for things remote. I love to sail forbidden seas." is not quite yet, but those other worlds, promising untold opportunities, beckon. Silently, they orbit the sun, waiting.
So that was some words that's in the book Pale Blue Dot by the scientist and communicator Carl Sagan. That's the kind of vision that motivates me to see what we can do. How can we actually turn that into a business plan? That's the goal of where you're trying to get to, and what are the steps it's going to take. Those worlds are there, and I'm not hitting right. Okay. Yes. So I want to start at the very beginning. What Mars was. If you ever as a child, I spent a lot of time. I grew up in upstate New York in a kind of darker, more rural part of the country. Spent a lot of time outside staring at the stars. And for most of human history, we stared up and saw the reddish glow of Mars as a point of light in the night sky. We saw its reddish hue associated with the blood and the gods of war, especially in the Western cultures, that saw the god of Mars, the god of war, amongst the stars. And for most of human history, that's all that Mars ever was. It was a concept of our imagination and a point of light in the night sky. And that changed for the first time in 1659 when we had a telescope that looked up and we had the first ever data set from Mars. And this here is the first ever data set where Mars is no longer a point of light. It's a sketch created by Christian Huygens in 1659. And for the first time ever, Mars is now a data point, right? It's a map, a planetary feature, a world that we can start to imagine. And then every 2 years, Mars gets kind of close, and our telescopes would point up and try and get more and more features. Now, if you had a telescope like this in a very dark area, this is about what you'd see. You see, a reddish glob, some dark areas. You can see this little triangular feature. That's probably what we map there. At the north and south, you can see white spots, and you start to see a world that's maybe not that different from what Earth might look like. We know we have polar caps just like Mars. We have dark oceans. Maybe these dark areas are, oceans surrounded by dusty continents. And not really knowing what's going on in this planet drove a lot of the early kind of understanding or thinking of what's going on. Some of the mapping led to mapping these features, channels, from Schiaparelli, who then was translated into the canals of Percival Lowell. And canals has a distinctly human formation. And this led to a lot of, even in the scientific community, that Mars may have been more Earth-like than what we know now, a place that might have oceans and civilizations building canals from polar caps to bring water to cities on a dying world. This led to the work by H.G. Wells, War of the Worlds, that was not ruled out by science in this era. And our view finally got closer when we sent our first ever spacecraft to the planet in 1965, the Mariner 4. This flyby mission was to get the first ever photos of another planet so we can start doing geology on another world. This here is the first ever photo of Mars from a spacecraft. Maybe there's oceans and forests or something there, we can't quite tell. And during this flyby, we got better and better images until we saw this was about the best image that this mission ever got. And this kind of rocked the scientific world. People who were hoping to find an Earth-like planet on Mars saw these impact craters. And we know well that there are very few large impact craters on Earth. Since this era, we found many, many more. So Earth has many more craters, kind of like Mars. But at this time, we didn't really know many on the Earth. But we knew the moon was absolutely full of impact craters. So if this image, all of a sudden Mars went from being an Earth-like planet to a moon-like dry body. And the chances of finding cities and civilizations kind of fell out of the scientific community. However, this is about 200 kilometers across photo. So you can see here, this is what the spacecraft, as it flew by, this was that first image I showed that was very from a steep angle, and then it mapped this line of images as it passed by, and then it flew on, so that's all we ever saw. And if you know Mars today, you've heard, the largest volcano in the solar system, Olympus Mons, that wasn't mapped. The largest canyon, Valles Marineris, wasn't mapped. The polar caps, they weren't mapped. So all these things were still in the future. All the wonders that we know now were not known in this early era. So as an example of where the kind of mystery could be, this is a 200-kilometer wide image of Mars. And so I'm going to show you a much higher resolution, but the same scale image. That there is a 200-kilometer wide image of Las Vegas. Some people say Las Vegas is habitable. So even, but from this distance, you can't really see it. You see a lake, Lake Mead there and some forest, but at this distance, maybe in the resolution, there's still a lot of stuff to be found. Carl Sagan, who narrated that opening video, after that mission, he still produced this image in a National Geographic article in 1967. So 2 years after we saw that Mars was more desert-like than Earth, he still posited that this is possible with that data. So, instead of oceans and forests, Mars is a desert world, a place that doesn't erode away craters. But in a desert world, you could still have Mars cacti and Mars bushes, maybe Mars jackrabbits running around. And so this vision of possibly, filling up our unknowns with life was a common habit of ambitious scientists who would look for money for more missions. So the next mission to go there was in the 70s, the Viking. These were actually going to orbit Mars and then land on the surface. They weren't expecting jackrabbits. If they found them, they'd be happy, but they were looking more for microbes. So there was actually experiments to look for life. They would take some soil, add some nutrients, see if life in the soil happens. And they landed and they found only rocks. And this is the view of Mars that a lot of us are used to seeing in pictures from NASA, pictures on the internet. And so we take this for granted, but this was a real shock to the scientists at NASA at the time. After a lot of effort of going to Mars, seeing Mars as the next step after the moon landings, a few years before this, the fact that Mars is a lifeless body after a century of trying to understand what life is there, this knocked the wind out of NASA's exploration efforts. And we didn't go back to Mars for 20 years. This mission created a lot of data, but there was basically a dark ages of Mars exploration. And it took 20 years for the analysis of this data to show us that Mars was way more interesting than we initially see. We saw evidence of massive floods and oceans, a really wet past. We've gotten meteorites that came back from Mars that we've been able to study to show that there's possibly even life in the earliest history. And so by the 90s, the politics and the science and all those pieces kind of came together to begin what is now a 30-year-long stretch of continuous study on Mars. So, there's a whole lot of stories in that. Let's see here, just dumped. In that story, so I don't have time to go through all the missions, but I wanted to show in this slide. So we see Pathfinder, Viking, the Viking I mentioned. Pathfinder was our return to Mars in the mid-90s. Phoenix, another mission, went a few 10 years ago now, I think, in near the North Pole. Spirit and Opportunity and Curiosity, more rovers. Not to mention an entire fleet of continuous observations from space: Odyssey, MRO, Maven, Mars Express from Europe. And so over the last 30 years, we've had a continuous robotic presence on Mars to map its history, map its composition, understand what rocks are there, and what does that mean for the evolution. There's a few more seats, I guess, up here if you don't mind sitting next to some globes. Yeah, so this is how we know Mars. We've basically invaded it with our robot fleets, and that has kind of set up kind of how we've learned about this planet. So Mars has kind of followed this kind of method to get to Mars. So after the initial Viking missions, we found evidence that there was lots of ancient water on Mars, and so we know life likes water. So maybe if we find geologically where the water was in the ancient past, we can find evidence of life and meet a lot of core NASA objectives. So that's when the early 2000s, Spirit and Opportunity, Odyssey orbiter, were trying to follow the water. That was the motivation of the sloganeering of those missions. We found lots of water. There was a joke, probably not so much a joke, but like the reality is, like, every week we found water on Mars. We found water on Mars. We find it as ice. We find it as in minerals. We find it as buried lakes. Again and again, water is all over Mars. But we never sent an instrument that actually looks for life since Viking, because when instruments fail NASA has trouble motivating the next mission. So we try to ask only questions we know we can answer, which is one of the challenges of the way NASA works. So once we know that life is there, water is there, we then send the instruments to actually look for habitability. Can water turn into organic molecules, into the energy, into the environments that life needs? That's what the Curiosity rover has been doing, and they have the instruments to say, yes, in this environment, we see organic molecules, we see the energy environments it needs for life to happen. We are now moving from looking for general habitable environments to actually finding seeking signs of life is the new slogan for Mars, where not only do we want to find places where life could be, but places where it actually existed. But NASA still has this challenge of not wanting to ask a question it can't answer. And so that is a little bit, I think, the motivation behind our next process of what NASA is doing to seek these signs of life. So we are going to do a sample return mission. So we're sending a robot to Mars to pick up samples and bring them back. And I'll talk a bit more about exactly how we're doing it. But after many years of work by me and a number of other scientists, we finally narrowed it down to where we're going to go to pick up these rocks. And we're going to this Jezero Delta area. So it's a large crater that was once a lake, and the river kind of flowed into this area and dropped these sediments. So these colors here are clay minerals. Most of Mars is volcanic basalts, not really a great place for preserving life or solving it. But here is where we have lots of clays. Clays are amazing at, well, clays, first of all, mean you have lots of water, enough energy to turn rocks into altered minerals, and it has really great preservation material. So if you're a petroleum geologist, you look for these deltas all around the world because they're a great place to find natural gas and oil deposits, and oil and gas are biosignatures of places where there was once life. So on Earth, we use these deltas to look for evidence of life, and so we're trying to use the same technique to look for places where life could be both kind of concentrated and preserved on Mars. So because bringing back samples from Mars is incredibly hard, just the kind of how much stuff you have to send to Mars in order to bring back something, we have huge engineering challenges. And so because NASA's Mars budget is only a few $1 billion every year, and that has to be divided up to pay for this about a $10 billion mission, NASA has broken down into 3 sections. So the first part of this is this one called Mars 2020, launching next year. That is this kind of Curiosity-sized rover, probably about this big, that's going to go to Mars, drive around, spend a few years picking out these perfect rocks. And so it's going to spend about 2 years picking about 100 grams of rocks. It's going to stick in little tubes. And the tubes can then sit on Mars until NASA sends the next mission. And this is going to go and pick up this cache of rocks and launch it into orbit around Mars. And we've never launched a rocket from the surface of Mars. And it sounds a little simpler. It's like Mars is smaller than Earth, so the gravity should be easier. But in order to send a rocket to Mars, we then have to have a much bigger rocket to send this rocket to Mars. So there's just you have to send the largest rockets on Earth end up sending a very small rocket to Mars. And one of the cool things that this process is doing is we're trying for the first time to build from what's on Mars. One of the experiments on the Mars 2020 rover going up next is how do we take the atmosphere of Mars and turn it into rocket fuel? How do we take some of the water molecules that are in the atmosphere and turn that into collection of rocket fuel that can be used to launch things? So the first test will just to see if it's possible, and if that works well, we're going to send a bigger version of this experiment on the next one and hopefully actually fuel the rocket with oxygen from the Mars atmosphere. Now there isn't much, but with enough time, it should be able to fill that. And so this will be the first time that we actually use the resources of Mars to help us do our things. So there's not a lot of oxygen in the atmosphere, but there's enough that with enough time that can do it. If we start to learn to turn ices and break that down into hydrogen and oxygen, then that'll be much more efficient. That takes more engineering, so we're not doing it on this mission, but for the first time ever, hopefully by phase 2, we can use Mars materials to help us explore it. And so then this will put the samples into orbit around Mars, where they'll be pretty stable until we finally get our third mission to go to Mars to pick it up and launch them back to Earth. And so that way we can see if these samples actually have biosignatures, fossils, trace fossils, whatever it is that life expresses on Mars, to look in the best labs on Earth we have. And so one of the fun parts about this is that this is an incredibly hard thing to bring samples back from Mars. And this architecture of 3 phases allows the effort to be spread into enough years that NASA can afford to do it. And the second side of it is that it gives a delay because, again, NASA doesn't like to ask questions we can't answer. And so now we need NASA to give us 3 different missions before samples come back in maybe 20 years before we know if it was like successful or not. And so that's a different generation of scientists who will then pay the price for this question. So that's the tactics that sometimes they play in order to get missions approved. And so this is the state of the art of what NASA and Mars exploration is right now. There's, SpaceX keeps talking about sending humans to Mars, but until they actually create a deadline that we can trust, I don't want to put that as like reality. Like I love the passion they do, and I'll spend a lot more time talking about SpaceX in a moment. But this, I would say, this first mission, that's definitely going to happen unless some disaster happens to NASA. The second one's already being funded. The technology's being built. The third one is well fitted in the budget. So this is the state of the art of bringing back samples from Mars for scientific study. And so the rest, yes?
Wouldn't it be cheaper to send like a lab there?
So the question was, is it cheaper to send the lab? The answer is no. Yeah, so the last mission we sent, the Curiosity rover, it's named the Mars Science Laboratory. So that effort was to try and take laboratory instruments, shrink it down so we could then look for habitability. But the truth is we don't have this technology yet to take state-of-the-art laboratory instruments, which are usually the size of lab tables or sometimes entire rooms, and put that on a rover well enough to decide. So we've had this debate a lot. So there's biosignatures, like we call it the signs of life, but there's actually at least 6 different fundamental types of what biosignatures are. Some are macrofossils, like the skull of a T-Rex. Others are little bacterial fossils. Others are just isotopic values or chemical values or mineralogical values. And so each one of those requires a different giant machine to say. So unless you know what environment you want to go to, which they didn't want to say because they wanted to keep it open during the selection process, you either have to shrink each one of those or you bring back the samples and then let another 20 years of state-of-the-art laboratory development on Earth be able to answer better. So there's another mission that I'm trying to propose that takes electron scanning microscope that's usually lab size, shrink it down to the size of a soda bottle and send that to Mars. So that's something I'm working on to try and do a little bit of that, but that has a lot of limitations in what type of biosignatures it can look at. It's really good for certain ones, but not good for others. So, so far our shrinking technology isn't good enough to be sure that we'll find what we're looking for. So if we actually want to know if these samples have biosignatures, bringing them back to Earth is the only way that we really trust. Okay, so yeah, that's what we know for sure. And so then the next is I want to talk about what are the future of space, how do we do the next steps to get more missions, more people, and all that. So that's where this, we have the Pathfinder rover, Spirit and Opportunity, Curiosity, Mars 2020, and then hopefully this next human step where we, humans themselves can actually experience the surface of Mars, bring back many more samples than the best rovers can, and bring all of our infrastructure to the surface. So one question I get a lot is, when will we get to Mars? And that is a tough question to answer. SpaceX has a number, NASA has a number, Mars One, that defunct reality TV show, they had a number. So you can say whatever numbers you want. The true answer is probably a $sign rather than a time. It's like how much money and put you into it. And so kind of just as an answer, I try to do, again, I don't know if it's right, but I think it could be, is about 5 years after we truly decide to go. And that decide, right? That's the key part, is when do we decide that the technology investment's worth it? When do we build the economy to make it happen? When do we build a culture that everyone is writing to their congressman and demanding that this is our first priority? So rather than saying, waiting for NASA or SpaceX to get their stuff together, I put it back to the people who are asking me the question, which is what good teachers do, right? They turn the question around. What? A pilot. How do we get a human to Mars?
No.
We. Yeah, the we is the collective human endeavor, the governments and the companies and all those pieces. Yeah, so this is to get a human to Mars, is I think 5 years after we as a side decide for the first human to get to Mars. This is how we get people to Mars, is by deciding a large enough entity of funding and culture and all those pieces that say that this is what we're doing. Yes.
So how much the cost will be?
How much will the cost be? Again, that's one of those tough questions. Different people. Yeah. So.
The decision is based on the budget.
Yeah. So the numbers that are the numbers are unknown for sure. But estimates usually peg it at about $100 billion and a lot of dedication. So, if you have more time, then the cost comes down a little bit because you can spread it out. If you're pushing, like when Apollo happened, that had about 9 years to get Apollo done. And they had basically unlimited money, but they had to build all of NASA infrastructure, right? They had to build the rockets, they had to build NASA bases, they had to build communication systems to talk to that. So there was a lot of infrastructure that had to be built from scratch for Apollo to happen. We have a lot of that technology already. We have a lot of rockets already in store. We have communication infrastructure. So a lot of the infrastructure is already there. We just need the resources to direct towards it. So as I just mentioned, how do we get to Mars? We need the technology to happen. We need the economy to push it, and we need the culture to really drive it. So these are some of the touch points that I want to talk about a bit over the next few minutes, and how some of the efforts I'm working on will intersect with that. So, SpaceX is all over the news. They love being in the news. They're doing great things. The technology that they're making is so obvious, right? Like they want to send reusable rockets to space. Like that's how we do everything else. When we first started sailing the oceans, we used reusable ships. We didn't sail from Europe to America and then throw away the ship. Well, I guess sometimes we did, and sometimes it crashed. But for the most part, we kept using it. We don't fly across the world and then abandon the plane, usually. Reusing rockets or reusing planes and ships and cars just is so obvious that we take it for granted. But for so long, all rockets were discarded after the single use. We tried to reuse the shuttle a bit, but that never quite worked. So SpaceX trying to take this kind of business culture of how do we use good economic advantages to just launch as much stuff into space as possible has been the key of their their survival so far, their economic success, and hopefully the push. By being able to land rockets and use them again, you now save $100 million every single flight. It takes a little bit of money to refurbish them, but as we get better and figure this out, we're just saving so much money per launch. Even these small things, like you probably saw landing a rocket on a boat, which is just it's kind of a cool thing, right? Like landing on a boat in the middle of the ocean. But this, the economics of this is just really interesting. Where if we launch from Florida, we usually launch over the ocean for safety and churn of the earth issues. And in order to land back on land, it takes about 17% more fuel to push the rocket against the churn of the earth to land back on land. If you send a boat out and land on your boat, you now save 17%. So the whole point of the boat is just to really push this economic efficiency for every single launch, to put as much fuel to getting stuff into space as possible. And so what SpaceX is working on is bringing down the cost of launch. For the last 20 years, Lockheed Martin, Boeing, the big United Launch Alliance is this kind of cabal of big rockets that NASA's been paying for. And they've been happy to just take NASA grants and launch stuff for the big players. And most launch costs are about $20,000 per pound of payload. And that has been the cost of going to space for decades now. And so SpaceX is working towards bringing that down by a magnitude. So they're hoping that once their system is working well, getting to space is now $2,000 per pound, which is still pretty expensive, but all of a sudden, you can now, with the same amount of money for launching, you can launch 10 times more stuff, more satellites, more experiments, more missions to Mars, whatever it is. If you can bring down the cost, the entire space system gets bigger. And the great beneficiary of this is how the larger economy works. All these small companies who have interesting idea of using space for economic good, for growth, but can't afford a $500 million launch, they can now launch, finding something for $50,000 fits a lot easier to try and fail. So it really just allows the entire economy of space to get better.
I had a question about this. So space debris is a big deal. India recently launched and knocked out a satellite that then could imperil some of the other stuff that's up there. So yeah, you can launch all kinds of stuff up there, but what is happening with all the stuff that's already up there?
Yeah, so space debris is, humans like to pollute. That's an issue wherever we go, and so there's a lot of good minds trying to solve that. Blowing up spacecraft for military demonstrations is like the worst way it does it. I know China did that. America has like a lot of space debris is just paint chips from American crafts, so they're not innocent by any means. So hopefully we have to have less to show this like national pride as far as blowing stuff up. There are some efforts to track the biggest pieces so we know where they are. There are some efforts to try and clean it up, but that's incredibly hard. So there are a number of startups, especially in the Bay here, who are trying to put the technology of how would you actually clean it up, what's the economic risks, trying to create the legal responsibility there, so that way if it's a piece of a Chinese mission that then blows up a commercial spacecraft, does that company have a legal case against the people of the debris? So there's I think if you start putting liabilities, people would be a lot more careful. One of the challenges before is that there was, space is so big, like you'd never fill it up. So a lot of people don't really worry about that because it's too expensive. But there are a lot of kind of very rapidly decaying orbits. Like if you launch stuff a bit lower, things will just fall out naturally and then burn up as beautiful little meteorites. So if you are more conscious about that, there's a lot of mitigation techniques you can use, building stuff that has less paint chips, more solid. So there's a lot of those things. So that's definitely a concern that we're trying to figure out. But like any human endeavor, pollution is one of those challenges that we need to thread through. So I don't have a solution for that. No one has a solution for it. But a lot of smart people realize that for us to get out, we need to solve it, and are working through a number of legal and technical and cultural changes that might change that. So, so SpaceX is continuing to build. So here's a nice little collection of like what rockets are coming out. We are now, what is it? In a couple of days, 7 days away from the 50th anniversary of the launch of Apollo 11. And they went up on this rocket, the Saturn V. So this is like a 250-foot tall rocket. The 3 people lived in this little cone. So that's like basically the entire thing that really went to the moon and back. There's a little lander that's stuck in here. But all of this is just to get this piece to the moon and back. And that's just because the rocket equation is a bitch. You have to get rid of a lot of fuel to get a little stuff to space. And so getting humans to space is going to take big rockets to just get out of Earth and figure that out.
So just to double down on that, the energy cost of just getting out of the gravitational envelope of the Earth, I think is one of the primary limitations.
Yeah.
You're talking $2,000 a pound optimistically.
Yes.
Which is what, $4 million a ton still?
Yep.
And just thinking of something weighs a pound and you have to lift it 100 miles. Think of that in terms of just energy.
Yeah.
What are alternatives? I mean, it really is a strong limit in terms of what you can get through the door.
That's a huge limit. So this is one of those things where we think about how hard it is, but I think about how hard it could be. So a lot of my friends, they study exoplanets. They look at planets around other suns, and there's all these super Earths. So like, Earth right now is this perfect size of it's being big enough where we have an atmosphere so we can have all nice life and all, but it's small enough that it only takes 26,000 miles per hour to escape. If Earth was a little bigger, this would be impossible. So first of all, I think myself that Earth is small enough that it's almost doable
but think
with a
of the
chemical rocket.
carbon footprint or the hydrogen footprint, whatever it is, to get a pound.
Yeah, so that is a challenge. Just people talk about space elevators. There's a number of hypotheses for how you
reduce the amount of energy.
Well, I think the whole idea if you build a space elevator, like that's a physical thing that then orbits between.
Yeah, but still, I mean, it's force per distance is work.
Yes, but that can be renewably powered because you can use electrical propulsion on a physical structure.
Yeah, sure.
So so again, like that is a challenge here. So you have to, if this was the only pollution humans do, I would say that's not a lot. But again, this is just another addition to what humans. So it's about priorities. It's about making this more efficient. So yeah, that is another problem that we haven't solved, and that is a challenge that part of our culture will have to decide if this is a sufficient use of our pollution allowance that we have to do. So yeah, this is the space shuttle that had up to like 7 humans launch. We see SpaceX's early Falcon 9s, the new Heavy they launch a lot, the Blue Origin by Jeff Bezos's company. They're trying to build their own rocket. So this is like the space launch system that NASA is trying to build to help NASA's government missions to space. So this is, most of these don't, let's see, this one existed, these exist. Everything else here is a fiction currently, and in the minds of billionaires. So
What percent of this is just fuel?
so on this one here, everything below this point is fuel. So like this here gets this part up to space, this part here gets this part up to a higher orbit, this part here basically kind of like propels this into kind of an escape trajectory, and then this part here is enough fuel to get to the moon and back. So all of this is to get like this part right here, about there. That is all that went to the actual moon. So everything else was to get this in the lunar trajectory. Yeah, so the mass problem is going to be a fundamental concern. And I will talk about one way we can help with that. Yes?
I'm just curious if there is any remote hope in fuels that have higher energy density than the ones we have now, or whether the chemistry and the physics of that is well understood enough that it's just never going to be possible.
So a lot of my, I am more of a geologist than a rocket scientist, a rock scientist rather than. But my understanding of the rocket equation is that, a little bit is energy efficiency, but a lot of it's just mass. Like you have to throw, you have to throw out so much mass to get the projection. So yeah, if you can go faster, so it's a mass of fuel as well as a velocity are like the two main factors there. So if you can really speed up the velocity of it, then you can do a little bit less mass, but that is something I haven't really heard a lot of dreams. So there's people who talk about electronic propulsion, but they just don't have the like they're great in space for turning electricity into propulsion, but the impact is not enough for launching right now.
The short answer is chemically, hydrogen with oxygen, there's nothing chemically that does better than that.
And luckily those are things that are very common beyond space or beyond Earth as well. Yes?
Would it ever make sense to use like a blimp or some sort of like balloon to get things up higher to launch?
So I think the idea for Virgin Galactic, they want to do like space tourism, where they take their spaceship up on a plane, fly it high, and then they can skip the early stages. And so there's a little bit of effort. I think that is challenging, and you start to be less efficient than the benefits of it. But I think having people think on those is better than not. But so far, I haven't seen big promise on that. Okay, so that pointed out a good question of how getting to space is hard. So let's assume that getting humans, getting civilizations, getting self-propagating civilizations beyond Earth is really hard and really expensive. But what if we can just send the most important things, like us? And so the rest of this talk is going to be talking about how can we build from what's already in space so we can start to bring much less stuff there. So one example of a company that's trying this effort is Made in Space. Started over here at NASA Ames. They built the first ever 3D printer to go on the space station. So now rather than, this is just a general little plastic 3D printer. The idea here is that rather than bringing every single tool you might ever need on the space station, so whatever breaks, you can now just send a file up. If you need to make a wrench to fix a bolt, you can just print that directly. Still doesn't save you mass because you still have to bring the print supplies and all that. But rather than bringing copies of everything you might possibly need, you can just bring the general material and then print out what you're actually using. And so that is still kind of experimental. It's working a few things now, and they're still trying to make it come. But for the first time ever, we can now build in space. They're also working on how do we build up the economy of space. So this one I think is really cool, is that they are now building fiber optics in space. So it's another little module that's on the space station. And if you are making fiber optics without a gravity field, you can make much cleaner, much more higher quality fiber optics than you can do on Earth. So the idea here is that you use space as the manufacturing spot. So you make it in space, make pure fiber optics, then bring it back to Earth, and hopefully the value of this really good fiber optic pays for the cost up and down. So that's, it still seems a little fictional, but the idea is like trying to make space integrated in the economy, make other reasons for going that isn't just bleeding taxpayer dollars to get up there, but actually letting the economic values drive it. So if that can work, that's really exciting. And so the future part of Made in Space is they're trying to build this Arcanet spacecraft where you can actually build structures. So rather than launching satellites and rays and all these things you want in space, you can send a spacecraft with printing material and it can construct it into space. That way, if you just send rather than, you can see it'd probably be very hard to send very large arrays on any rockets that we currently have. But if you send like a big mass of printing material and then print it, you can have a lot more variability. You can have smaller rockets build very large structures. You still can't get around the mass. And then the next step of this is using materials you can get from asteroids. If you can use the rocks and minerals that are already in space, you save the entire weight of construction. And so that is in situ resource utilization. ISRU is a major research area of NASA of how do we use the materials of space to make stuff. And I'll be talking a bit more about that. But a bit about the just space economy. This is a space fund trying to show which of these space companies, there's hundreds of space companies now that are trying to figure out their business plans and get investors and all that. But this one tries to list as many as they can and try and figure out which ones are real. Like some are seriously using money to make new technology, others are kind of the games that people play. And so they're trying to figure out which ones are real, which is a challenge. So they have ones on transportation, these rocket companies, there's many of them. We know SpaceX, Blue Origin, there's ones of all different scales. Communications and human factors, supply chains, energy, all these different industries that are now growing in space every day. I'm going to talk about two efforts that I'm doing that kind of relate to parts of the key aspect I mentioned before. Made of Mars, it's my effort to work on the material side of this learning, and Astral Reality, which is another effort to try and communicate the cultural side of it. So Astral Reality is the one that makes these models of the planets. I have them up front. I encourage you to come up afterwards. Augmented reality kind of adds data to it. The point there is how do we turn physical, how do we make these places real? That whole idea of how do we turn Mars into a real place, a destination, having the culture of people who want to go. And by putting planets in your hands, on your shelf, this is now something you just can't ignore. It's not an app that you don't have to open. It's a physical thing that reminds you that these are places that hopefully you want to go and get you thinking and keep them active in our minds. I won't talk too much more about that right now because I want people to come up later. But for Made of Mars, the idea is how do we build from the materials of Mars? If we want to build bases on the Mars, Moon, asteroids, these are all put up by ideas of some people. SpaceX wants to go to Mars, NASA wants to go to the Moon, Jeff Bezos wants to build in deep space, most likely from asteroid materials. And how do we actually do that? So going back to Mars, this is my bread and butter, what I've learned on. This is a geological map of Mars, and I spent a lot of my life kind of mapping the minerals of this planet. And so these red areas here, these are giant volcanoes made of volcanic basalt. The same rock that makes up Hawaii and Iceland can be found covering half the planet, but there's also basalt in the north. And even this area here that's not pure basalt, it's kind of an altered basalt clay because of the history of water. And these are all resources that we are familiar with. There is nothing on Mars that we haven't had on Earth. So we know what these materials are, we know what to work with them. So just like some of the main types of materials that we found on Mars, basalt, volcanoes, clay deposits, gypsum deposits, hematite, and we already know how to work with a lot of these. We can make iron, steel products from hematite. We can make drywall and molds from gypsum. Clay can be used for all sorts of ceramics, 3D printing mediums, and basalt is the one I'm going to talk more because I'm a volcanologist. We can turn basalt into fabrics and fibers into building materials. I have a number of materials up here that you can feel that are made from volcanic rocks. But besides Mars, the near side of the Moon, the Mare, that's all volcanic basalt. There's an S-type asteroid that makes up 18% of all asteroids. That is almost pure basalt. It's incredibly common on Earth. Here's my favorite little volcanic basaltic volcano in the Mojave Desert, a few hours away from here. If you ever want to go lava tube caving, there's all over there. Between LA and Las Vegas, it's just sitting there waiting to be explored and pick up your favorite rock. Basalt's found all over the planet in these giant deposits, so it's very common. It turns out we can take volcanic rock, turn it into gravels, melt it back into lava, pull it into threads, and then weave it together into fabrics. We can take these fabrics, twist it into rebar for construction, into a number of other projects. I have rebar up here if you want to feel how volcanic rebar feels. And so from this material, we can apply our ingenuity of design, of manufacture, to create physical structures, things that we need. You can build, composites for spacecrafts, for buildings. And this is the material that we'll have. And rather than bringing everything with us, we can use what's already there. So just another beautiful shot of what these rocks are. You can feel them up front. already this is being used in the economy, used as like a base for for snowboards, for boats, for construction, as composites in cars. It's a place where if you want to use carbon fiber, but you want something cheaper, you don't care about being so light, basalt fiber kind of fits that market niche. So how do we expand that, learn to make more things out of it, so when we get to Mars, we can make entire cities out of the materials that we see.
So I'm curious, from a chemical point of view, what is basalt?
So basalt is an iron magnesium silicate. So basalt is a rock full of many minerals, olivine, which is iron magnesium silicate. It's made of pyroxene, plagioclases. So it's basalt is a rock that when you melt it and quench it, it becomes a glass. So an amorphic glass with high iron contents.
So you don't have to reduce it to
No, so it's kind of like fiberglass, but the iron in it allows it to flow a lot better. So it still has some of the challenges of fiberglass, but it's a lot.
In short, we're working with glass fiber.
Yes, so it is a glass fiber. For all the good and bad that comes with that. So this is how I met Kitty. Is I saw her beautiful space designs. I figured maybe she'd be interested in a material that was related to space. So I think she did an amazing work trying to show how this material can be made beautiful, interesting, tell the story of it through design. And so that's what I'm trying to do with Made of Mars is see how this material might be used both for industrial purposes as well as the things that inspire us and get us excited to design and build. Right now this is like a beautiful little thing that gets you to think and say, wow, a volcano can make into a dress. But on Mars, if we can make clothes out of this, that will just save us bringing everything. That saves us, millions of dollars of transport costs if we can make locally throughout the solar system. So I see this as a pathway forward to building beyond Earth. For now, it's a beautiful way to share this adventure of space and the geological lessons.
It's gotta be fashionable in space.
Of course, of course. So that's the goal of Made of Mars is how do we really refine this. I'm trying to create some products. I have a few examples of things I'm trying to develop, trying to find the right product fit, find the right interest, and then doing some melt experiments. How do we make the materials more versatile? How do we add different colors? How do we recycle it? How do we make it more sustainable on Earth? And then use this to make better factories on Earth that we can then package up, launch to the moon, launch to Mars, and build on. So that's the vision of Made of Mars that I'm working on, where we can turn volcanoes as our pathway to Mars, and there's a little geologist there looking to make the next big thing. So we have products on Amazon Handmade. If you want a little keychain, I have examples here if you feel like taking one home for $10. And I'd love anyone who wants to follow my work, feel some astral reality. I'll be here for some questions or can take some from the group. Yeah. Thank you.
Hi. Is anybody building machines that can construct this habitat in a kind of unsupervised, automated way on Mars or Moon?
So there's definitely people working on habitat construction. So NASA has this Centennial Challenge where they get student groups and engineering groups to usually use 3D print, like large-scale 3D ceramic soil printers. And so one company based in New York, they just won the competition, and then they launched a Indiegogo to actually fund the building of a structure like this and then offer it as an Airbnb. So I don't want to quote how unsupervised that is because they definitely had people like around it to make sure. So it's probably not ready to just blast off to Mars yet, but it's that first step of being able to use a Mars-like simulant in a kind of very contained construction process to build what you need. So the first steps are happening, but I think it needs probably a bit more development to make it fully unsupervised.
Thank you.
These globes are nice and solid, so it's okay. If people want to come up, so I have basaltic sleeves and ropes and keychains. You can feel the fabrics. It all comes from a volcanic basalt I picked up in Hawaii. Also have astral reality planets and things if anyone feels like bringing a planet home. Feels like a rock. Yeah.
Awesome stuff.
Thank you.
Very exciting.